Hi, friends. It's my pleasure to introduce our next speaker, Igor Malovitsa. Igor from Ukraine. He is a software developer with expertise in Rust, JavaScript, and Python. He also a co-founder of our community and an integral part of the team of administrators, evangelists. He took active role during organization of the conference, and also he has a role of speaker this time. Also, he is a mentor at Rust Camp, who, for those who may not familiar, Rust Camp is an intensive bootcamp organized by our community twice a year to prepare participants for professional Rust development. If you didn't hear about it, you can apply to the next winter Rust camp. In his talk, Exploiting MapleStory RNG for Fun, Igor will dwell into how to exploit a cute MMORPG by leveraging a weakness in its random number generator. The exploit allows for unusual favorable outcome in game's lottery system, and due to requirement of time and space, Rust proved to be ideal choice for the implementation. Please join me in welcoming Igor to the stage. Igor, please.
Thank you, Konstantin, and thank you for your warm introduction. And I'm going to start the presentation. So, welcome. My name is Igor, and I like to make software go fast. I enjoy reverse engineering and origami. My language of choice is Rust, and that is why I mentor students in Ukrainian Rust Bootcamp. And today we're going to talk about adventures in exploiting a game called MapleStory in some weird and exciting ways. But first, this was a collaborative effort between me and Brandon Falk, also known as Gamozo. He is a hacker. He can find zero-day bugs in any obscure environment, set up fuzzing for any system, and he develops operating system because everything else is just way too slow. In this specific project, I took the role of doing the mathematical point of the mathematical part of the system. So I developed the algorithm to break RNG, and Brandon Falk is both responsible for all the heavy lifting. So making sure everything works correctly, making sure the game can run and execute all the necessary commands for us to do. So let's talk about our target. MapleStory is a silly old multiplayer game where you can fight monsters, level up, and chat with your friends. As you can see on the screenshot, it has very cute graphics. It's very cute. So let's take a look at some of the gameplay. So in this case, you can see the main character is interacting with NPCs in order to buy and enhance weapons. Later, we can scroll later and we can see that the character is also using weapons, and these weapons can be used to fight monsters. A disclaimer: we are not doing this for illicit gains or to get an unfair advantage. However, since MapleStory is almost completely controlled from the client side, Gamozo has previously demonstrated how to exploit MapleStory by manipulating the client memory and network protocols. So today we are aiming a bit higher. Our target is to subtly manipulate the server state for our advantage. Let's take a look at the state-of-the-art MapleStory hacks. So in this video, you can see main character killing every monster on the screen and collecting all of the loot. This is not supposed to be happening. However, because MapleStory is completely controlled from the client side, this is possible. However, this is very easy to detect because many actions performed by the player are easily detectable by scripts. So what we're going to do is we're going to introduce a hack which is not detectable in this manner. So what are we aiming at? We are aiming at a specific mechanics which is called enhancing or scrolling weapons. So you can enhance weapons to increase their damage. However, there is a chance that your weapon will get destroyed or get a bad improvement. As you can see on the screen, the person is using scrolls in order to enhance a weapon, and eventually one of the weapons completely gets destroyed. Let's take a look at this schematically. So we have a process of enhancing, and there is a 90% chance we can get a bad improvement or 10% chance that we get a good improvement. So for one step, it's going to be 10% chance of getting a good outcome. However, there are 10 steps of enhancement, and these percentages stack up exponentially. So they are multiplied. So you have 1 in a billion chance of getting the best weapon possible after 10 enhancements. Well, how do computers roll dice? Almost all of the so there are such things which are called pseudorandom number generators. Usually they have some internal state which is not accessible from the outside, and they have a function which updates this state, and eventually that state is transformed into the output number. So this loop creates a list of output numbers. However, all the steps here are deterministic. So once you know the algorithm and you know all of the state, you are able to predict the outcomes, and you can win at the lottery. Please do not do this in real life. So how does the random state generator look like in MapleStory? This is a Rust adaptation of the MapleStory RNG. As you can see, there are 3 independent state fields, and they are updated in an independent way, so they do not intermix with each other. However, when the RNG outputs its value, all the RNG states are mixed together using XOR or exclusive OR. All right. Since we are lazy, we decided everything. They had to do something which every lazy hacker does using in a CTF. We are going to use a Z3 solver. What is Z3 solver? Well, it's a wonderful tool which helps you find solutions for symbolic equations. So, for example, you have a function which checks whether or not a specific key is a valid key for a game. And Z3, in principle, can reverse that function and it can give you a valid key for a game sometimes. So Z3 is called an SM key solver, and you can look at this here, and there are also Rust bindings. So giving any binary formula, it can tell you whether or not there are solutions for this binary formula. Most of the time. That's not technically always possible. So how is this going to work? Well, we're going to give symbolic equations which correspond to the RNG state updates, and we're going to give it RNG outputs. Z3 solver will give us RNG state. All right, great. So we're going to translate our RNG into some form which is understandable by Z3 solver. We're going to feed it all the outputs, and we have the RNG state. Excellent. But there is an issue. We would like to do it in real time, and this solver takes a lot of time to actually do this. So we would like to have something which gives us answer. How would we calculate these values? Well, we would like to ask Z3 to do it. But Z3 does not support giving us symbolic answers. So what we decided to do is take a look at how Z3 transforms the RNG state symbolically. And as a result, we have this as a single bit output from RNG state. It's really hard to read. However, we can simplify it a lot. As you can see, this is only only some bits selected from the state, which are XORed together. All right, so let's rewrite it in a way simpler way. So we have the first output bit is going to be a XOR of some specific bits in the RNG state. And we can write down the sequentiation for every output bit. All right, so where does it get us? Well, so far, not much. Let's do some transformations some more to make it more understandable and to use mathematics some more. We are going to use this notation in which we are going to say output bit 1 is going to be our O1 and state bit 2 is going to be S2. So we have this symbolic equation in which we have several output and input bits. It's still not as nice to work with, so we would like to do some transformation in order to make it in a more uniform state, because working with symbols is hard. We would like to work with numbers. Let's introduce 0 bits. So in this form, we have a table of bits 0 or 1, which are going to turn on or off any specific bit. So, for example, in the output bit 1, the first bit of the state does not influence the output. And therefore, S1 and 0 is going to be 0, and it's not going to influence the output of XOR. This uniform representation of these equations allows us to think about this in a different way. It allows us to think about it as if these were linear equations. It's because the output bits are a linear combination of input bits. And once we have this, we can reverse it. Let's see. So we have RNG state on the top, and we have RNG state on the right. So this table is a matrix, and we have a vector of bits. Using XOR as a linear combination and using a bit binary end as multiplication, we can use this as a basis for our linear algebra. Once we have a matrix which updates the state, we can magically find the inverse of this table, of this matrix, and which allows us to transform RNG output into RNG state. And symbolically, it would be represented like this. So we have output equals RNG state times update matrix. We can multiply both sides by inverse of the update matrix. And then therefore, we have RNG state is equals to output times the inverse of update matrix. Right. So once we have the equation to solve it, we will need to put the entirety of this exploit together. So this is only the mathematical side. How does this work in principle? On this diagram, which is UML interaction diagram, we have 3 actors. First, we have the server, or the game server to which we are connected. It's a secure environment to which we do not have no influence except for the game mechanics. We have an oracle, who is a specialized client who will be able to determine the RNG state of the server. And we have the gambler, who is going to benefit from knowing the next RNG state. So the gambler is going to play a lottery and win. How does the exploit work? First, the oracle is going to initiate 30 teleports, and the server will respond with 30 random locations. Each random location gives us 3 bits of value. So we take these 30 times 3 or 90 bits of value, and we reverse the RNG state, because RNG state is exactly 90 bits. Once we know the RNG state, we can know in advance that there's going to be some value in the future which is beneficial for us. We advance the RNG by a specific number of steps, and we signal to the gambler that the next RNG is going to be beneficial for the gambler. And the gambler initiates the action, in this case, to enhance a weapon, and the gambler gets the best enhancement. All right. All this sounds good in theory. In practice, there are other players, and other players can initiate RNG rolls at any point. So how often does this happen? Well, we have observed from reversing the RNG state that there are 1.7 billion RNG updates in 32 days. This averages to about 615 rolls per second. So do we have to be able to do our exploit in 2 milliseconds? Not really. Why? Because there are many actions, for example, killing a monster, which initiate several up to 40 RNG rolls. So in practice, we have on average 60 rolls, on average like 40 or 60 rolls per second, which averages to about 66 milliseconds per different 66 milliseconds interval between different RNG rolls. Okay, so we have approximately 60 milliseconds to do our exploit. How long does it take to do it? Well, it takes 1,000 cycles on the modern CPU to break the RNG, and the rest is purely networking. So in order to minimize the chance of any other player interfering, we had to position the machines which were exploiting the RNG as close to the game server as possible. So it was just basically finding the appropriate AWS redundancy location. Right. So this exploit was successful, and there was the best weapon was obtained. So great, we have an exploit, and we have proved ourselves that we actually can break the RNG. What can be done about it? Well, the obvious answer is to use a cryptographically secure random number generator, which is by definition cannot be broken in this way. You can rate limit the user actions, and rate limiting user actions allows you to understand whether or not there is an automated bot working on the other side. You could monitor suspiciously active users. You could monitor suspiciously successful users. And these systems are not hard to implement in. In this specific case, the game was using C# as its server, and there is a built-in standard library cryptographically secure random number generator, which is hard to break. Interestingly enough, if you use the round crate is using a relatively secure random number generator by default, which you cannot break in this manner. And why do those games choose not to? I don't know. Maybe it's because it's old, maybe because they're not considering it to be a security issue. But anyway, MapleStory is a very old game. It's broken in so many wonderful ways. And we find a way to break its RNG without actually hurting the game too much. Casino websites are definitely aware of these exploits, and they know how to use cryptographic secure RNGs. So MapleStory maybe should learn from this. If you're developing RNG, games which involves RNG, please be aware of these exploits and please use more secure RNGs. When we were developing these exploits, we ran into several dead ends, and the mere fact that we didn't give up gave us this result, gave us this very cute, very fast exploit. So don't give up. And I learned mathematics and I love to use it, and it was useful in this specific case. You never know when your skills are going to be useful. This is the end of my presentation, and we can go to Q&A.
Thank you, Igor. Let's check what question have you received. We have few. Okay, the first question, which was answered, but I will ask it anyway. So the RNG state is unique for each player. Can you clarify it once more?
So the RNG state is global for all players. So if the other player picks a value from the RNG state is updated and other players can see it. And that, so when I was talking about these 1.7 billion roles, these roles are shared between all players.
Yeah, thanks. Another question. So it was not really clear for some listeners. You have to know the number are generated from server state, or you use Z3 with server output. How do you use Z3? The
Right. So in this
relationship between
So
all of
in this
these things.
specific case, right, if I understood the question correctly, so how do we do it? So here on the screen, you see that there are several numbers, right? So what we can do is take 90 of these numbers or 30 of these numbers, and we take the bottom 3 bits. So we just take each number modulo 8. And this allows us to reverse the RNG state. So basically, the bottom 3 bits are going to be a linear combination of the RNG state. And once I have the update matrix, I can reverse the linear combination. So in this case, I take 30 random numbers, and the bottom bits are something which I can directly use.
Okay, help me to clarify. Do you or don't you use Z3 interactively? You use Z3 once, and after you find out the formula, you don't need Z3 anymore. Or you use it interactively, Z3, I mean solver, to...
Oh, so in this case, okay, I did not understand correctly. So D3 is too slow to be used interactively. It takes way too much time to do it. Z3 we used as a tool for investigation and a tool to discover what's useful. So in this case, when we used the V3 allowed us to see this formula. And this formula basically gave us insight into how the bits are transformed.
Yeah, and how much time does it take to find out the formula of computation?
So for Z3, it was about a second. So it's not usable in real time for this purpose.
Still pretty fast.
Well, it is fast. However, it's 40 times slower than it needs to be for this purpose.
Yeah, and related question. So did I understand correctly? You used Z3 to derive the matrix equation. I usually just put as check instead of looking the equation.
Right. So the matrix was not generated from S3, but from Z3. The matrix was generated by manually constructing. So I actually have the code here, which generates the matrix. Let's see. Right. So the code is right here. So what it does is it takes the matrix and does these manipulation of the matrix. And that basically these manipulations directly correspond to the operations which are so these operations on the matrix are directly corresponding to these operations which are on in the RNG. So this generates the update matrix.
Okay. Luis, if it doesn't answer your question, you can ask one more, or well, how many questions you want. Another question from Mark. Didn't you say that 60 milliseconds is average, but still an an action from another player can break your exploit.
Correct. An action from another player can break the exploit. So this is why we have to minimize it by minimizing the latency of our communication. And yes, so that's why you have to minimize your risks. There is a risk that it will fail. However, we were able to do it up to as many steps as necessary. So it was good enough.
And if we are more number oriented, good enough is what? What percent of success using the exploit is? Is it like one less than percent, or you reliably can apply the exploit in most cases?
If I understand the question correctly, how reliable is the exploit? And in this case, the exploit was reliable enough to enhance the weapon to its maximum. So the exact probability we don't know. We didn't calculate it. It's possible it would fail at some point.
I mean, not very precise number, but what a degree of digit we are talking about? One of thousands, one of million, one of
I think
10.
I think it would be closer to 1 in 100, 1 in 200. So you would be able to enhance a weapon about 100 times before you would fail.
Okay, so it's very high. And regarding timing, do you take into account time of day to minimize risks of failing because of other players?
I've been thinking about this concern. I don't know whether or not it was used. It's like it was likely used, but I'm not aware of it.
But in your specific situation, did you take the time of day into account?
So the end exploit was done by Brandon Falk, and I'm not sure about the density of players and whether or not he accounted for it.
Okay. And this exploit is applicable only to the MapleStory. And I will extend the question. Is this technique applicable to other games and non-games services? And if so, what criteria is to apply it?
All right. So the question is, can we apply this exploit to other games and other places? So there were several examples in the past of gambling websites having broken RNG. And it was in 2000s, it was in 1990s. Basically the gambling websites, the online casinos didn't know how to generate random numbers, and it was actually possible to predict what was going to happen. And people have exploited these in the past. This specific approach, the code we are using, may not be useful for other games. But this approach of understanding the RNG, being able to reverse it from the output, is applicable in all other places where RNG is weak. I hope this answers the question.
Okay. Rephrase the question if it doesn't, Dennis. Next question from Bogdan. Can we use it for Dota 2, where we have a character and critical strike, which depend on a chance?
So the short answer is yes, but the long answer. So Yes, it is possible to use it in Dota to gain crits, and but Dota has other exploits because you have some time in Dota specifically. You have some time between you initiate the attack and the attack being propagated to the enemy. So when you initiate the attack, the server will tell you this attack is a crit. This attack is a critical attack, and there are plenty of bots who initiate many attacks until you get a crit, and they release the attack only when this attack is going to be a crit. So there are exploits which do similar things, but in Dota. I hope this answers your question.
Yes, thank you. By the way, Igor, please check chat. Meanwhile, I'm reading the next question. Which RNG from rand crate or any other crate would be better to use in a game?
Basically, the default RNG would be pretty fine. I'd have to look up the specific algorithms which are used. I actually can't remember any of the names. So
And yeah, and what is best practice for security? Is it better to have a state per user or global state? I guess global is more secure way.
I don't like actually it is first it's a broken question in itself. If you have an RNG in which this gives an observable difference, this RNG is already broken. All right, meaning if you can spot the difference between RNG being global and RNG being per user, that RNG is already broken. It's not cryptographically secure. And the answer is you'd have to use cryptographically secure RNG. There are weaker RNGs which can be used, and those weaker RNGs would be still hard to predict.
And still, if answering a given short answer, is it a yes or no? What is better, to have global state or local? As I understand from your speech, it is better to have a global because then hackers have harder time to find weakness because other players influence the state. Am I wrong?
Sure, if you have a weak RNG and if you're updating your RNG frequently, it would be harder to use this specific exploit. I don't think this is a good solution for the issue you're facing.
So basically it is a bad solution anyway, and it doesn't matter it's global or state per user.
So I would say that global and local state both have advantages and disadvantages, and those are unrelated, I would say unrelated to security.
Okay, the next question, how else can Z3 be useful when looking for vulnerabilities?
All right, excellent. So Z3, you can feed it symbolic representation of, for example, of a binary function which you're inspecting, and it can give you possible inputs to this function which would trigger some bad behavior. So Z3 allows you to find mathematical solutions to constraints which you give it. And I gave you an example of a keygen because Z3 can solve some keygens. Z3 can find some vulnerabilities in functions. And that is how it, in principle, can be used to find vulnerabilities. Or for example, another example would be finding hash collisions. You can, if you have a weak hash, Z3 can give you answers to collisions to a weak hash.
All right. Comments from Mark. So it's like fuzzing, isn't it?
No, it's different from fuzzing, but it uses some similar techniques sometimes.
What is difference? Can you explain simply?
Z3 has many heuristics which allows it to find solutions to binary equations, and some of those techniques do involve trying out some random paths, and trying out random paths and trying out different permutations is what fuzzing does. And Z3 has many other heuristics which are completely unrelated to fuzzing.
I see. Thank you, Igor. That's it. No more questions. Thank you, Igor, for this interesting speech on topic of hacking. It was interesting to listen to you. Thank you guys for your questions. Igor, anything you want to add?
It's been a pleasure being here. I hope you enjoyed this talk. I hope you do hacking for good.
Thank you, Igor. See you guys.